Why does keras model predict slower after compile? In theory, the prediction should be constant as the weights have a fixed size. How do I get my speed back after compile, without the need to remove optimizer? See associated experiment, this URL.
Update, the 15th of January 2020. The current best practice for small batch sizes should be to feed inputs to the model directly, i.e., preds equals model X, and if layers behave differently at train, inference, model X, training equals false. Per latest commit, this is now documented. I haven't benchmarked these, but per the Git discussion, it's also worth trying predict _on_ batch, especially with improvements in TF 2.1. Ultimate culprit, self._experimental_run_tf_function equals true. It's experimental, but it's not actually bad. To any TensorFlow devs reading, clean up your code. It's a mess. And it violates important coding practices, such as one function does one thing, _process _inputs does a lot more than process inputs, same for _standardize _user _data. I'm not paid enough, but you do pay, in extra time spent understanding your own stuff, and in users filling your issues page with bugs easier resolved with a clearer code. Summary, it's only a little slower with compile. Compile sets an internal flag which assigns a different prediction function to predict. This function constructs a new graph upon each call, slowing it down relative to uncompiled. However, the difference is only pronounced when train time is much shorter than data processing time. If we increase the model size to at least mean-sized, the two become equal. See code at the bottom. This slight increase in data processing time is more than compensated by amplified graph capability. Since it's more efficient to keep only one model graph around, the one precompile is discarded. Nonetheless, if your model is small relative to data, you are better off without compile for model inference. See my other answer for a workaround. What should I do? Compare model performance compiled versus uncompiled as I have in code at the bottom. Compiled is faster, run predict on a compiled model. Compiled is slower, run predict on an uncompiled model. Yes, both are possible, and it will depend on 1. Data size, 2. Model size, 3. Hardware. Code at the bottom actually shows compiled model being faster, but 10 iterations is a small sample. See workarounds in my other answer for the how-to. Details. This took a while to debug, but was fun. Below I describe the key culprits I discovered, cite some relevant documentation, and show profiler results that led to the ultimate bottleneck. Flag equals self.experimental_run_tf_function, for brevity. Model by default instantiates with flag equals false. Compile sets it to true. Predict involves acquiring the prediction function, func equals self.select_training_loop x without any special calls, cast to predict and compile. All other flags are such that a. Flag equals true, func equals training_v2.loop b. Flag equals false, func equals training_arrays.array. Like training loop. From source code docstring, A is heavily graph reliant, uses more distribution strategy, and ops are prone to creating and destroying graph elements, which may impact performance. True culprit _process inputs accounting for 81% of runtime. Its major component _create _graph _function 72% of runtime. This method does not even exist for B. Using a mid-size model, however, _process inputs comprises less than 1% of runtime. Code at bottom, and profiling results follow. Data processors. A. Class TensorFlow.Python.Keras, Dungeon.Data_adapter, tensor-like data adapter used in _process inputs. Relevant source code. B. NumPy.NumArray, returned by convert_eager_tensors_to_NumPy. Relevant source code, and here. Model execution function, for example predict. A. Distribution function, and here. B. Distribution function, different, and here. Profiler, results for code in my other answer, tiny model, and in this answer, medium model. Tiny model, 1000 iterations compile. Tiny model, 1000 iterations, no compile. Medium model, 10 iterations. Documentation, indirectly, on effects of compile source. Unlike other TensorFlow operations, we don't convert Python numerical inputs to tensors. Moreover, a new graph is generated for each distinct Python numerical value. For example, calling G2 and G3 will generate two new graphs. Function instantiates a separate graph for every unique set of input shapes and data types. For example, the following code snippet will result in 3 distinct graphs being traced, as each input has a different shape. A single tf.function object might need to map to multiple computation graphs under the hood. This should be visible only as performance. Tracing graphs has a non-zero computational and memory cost, but should not affect the correctness of the program. Counterexample. Outputs.
Update, see actual answer posted as a separate answer. This post contains supplemental info. .compile, sets up the majority of TF/keras graph, including losses, metrics, gradients, and partly the optimizer and its weights, which guarantees a notable slowdown. What is unexpected is the extent of slowdown, tenfold on my own experiment, and for predict, which doesn't update any weights. Looking into TF2's source code, graph elements appear tightly intertwined, with resources not necessarily being allocated fairly. Possible overlook by developers on predicts performance for an uncompiled model, as models are typically used compiled, but in practice, this is an unacceptable difference. It's also possible it's a necessary evil, as there is a simple workaround, see below. This isn't a complete answer, and I hope someone can provide it here. If not, I'd suggest opening a GitHub issue on TensorFlow. Op has, here. Workaround: train a model, save its weights, rebuild the model without compiling, load the weights. Do not save the entire model, for example, model.save, as it'll load compiled. Instead use model.save_weights, and model.load_weights. Workaround 2, above, but use load_model path, compile equals false, suggestion credit, D. Mueller. Update: to clarify, Optimizer is not fully instantiated with compile, including its weights and updates tensors. This is done when the first call to a fitting function is made, fit, train_on_batch, etc., via model._make_train_ function. The observed behavior is thus even more strange. Worse yet, building the optimizer does not elicit any further slowdowns, see below, suggesting graph size is not the main explanation here. Edit: on some models, a 30x slowdown. TensorFlow, what have you done? Example below. Outputs: